From the RSNA, this is the Radiology Artificial Intelligence Podcast. My name is Paul Yee, and I'm a radiologist at the University of Maryland and the host of the podcast. On today's episode, we'll be talking with a radiologist who also happens to be an AI software developer with real-world experience clinically deploying AI. Our guest today is Dr. Akshay Goel. Dr. Goel is a self-described AI researcher, software developer, and radiologist with experience creating AI-based medical software. He has built lab-first deep learning and computer vision pipelines and has led development of a cloud annotation platform for Radiology-AI. He completed medical school at the University of Texas Southwestern, where he developed its first automated pipeline to calculate aortic stiffness MRI markers in over 1,800 patients. After a radiology residency at Columbia University, he did a one-year body MRI fellowship at Weill Cornell Medicine, where he spearheaded the development of an AI segmentation pipeline for polycystic kidney disease that's currently used in clinical deployment. Akshay is the founder and CEO of a company, Radiology-AI, that supports multi-user annotation of CT and MRIs using a state-of-the-art browser-based annotation software, and he is currently senior machine learning scientist at Tempus Labs, a company working on data-driven precision cancer imaging solutions. Akshay's experience spans clinical, technical, and business realms, and we are lucky to have him here on the podcast today to share his thoughts about AI in radiology and his personal experiences developing and deploying AI in clinical practice. Akshay, thanks so much for being here on the Radiology Artificial Intelligence Podcast. Someone who I consider a good friend. It's really great to have you here and really looking forward to talking to you today.
Yeah, Paul, it's always great to catch up. So I'm super excited to be on here.
Yeah, so your background is really unique, Akshay. You're a fully trained radiologist with a specialization in body imaging, but you're also a software developer in addition to a startup CEO. And so needless to say, you wear a lot of different hats. Can you tell us and our listeners about your background, what got you into informatics in general, and more recently in AI and machine learning?
Sure. Yeah. So that's a really great question. My entire journey was really just kind of a kind of step-by-step exploratory process. It actually started off in high school. I naturally gravitated towards technology, and my high school actually offered programming curriculum. So I kind of got really deep into programming in high school, but I also have a uncle who's a physician, so I was very excited about medicine. So during college, I actually kind of had two focuses. I was doing CS, but I was also shadowing doctors, volunteering at UPMC in Pittsburgh. I went to school at Carnegie Mellon, and so ultimately, kind of at the end of college, I made a decision to pursue medicine, and I'm really excited I did that. It's been a lot of fun, but along the way, I've always tried to re-engage in technology. I think you could relate to this, but small research projects, things like that. I did some more sizable work. I took a year of research during medical school, working at UT Southwestern on aortic segmentation, and that was a year where I was like, I remember telling my wife, at that time she was my girlfriend, but I remember telling her like, hey, I really have to be involved in technology during my career as a physician because I really love it. And there's something about, I think, building some technology and then seeing it work on a large scale that is really exciting. So at UT Southwestern, I was working on a project for a database of 1,800 patients. But I think that that's the exciting thing about technology is that it scales. And I think that in 2022, that's really obvious as you see all these companies launch really kind of high scale products.
Yeah, that's really interesting. I think a common thread that we often see in people in our positions as radiologists working in AI is this interest in technology and seeing how it can impact, our field and beyond. So can you talk a little bit more about how this happened in radiology? So obviously you went to radiology residency, you did fellowship.
Exactly.
You did varying, I know we were informatics fellows together, so I'm wondering if you can talk about that a little bit.
Sure. Yeah. So that journey kind of continued. So I picked radiology for both, like, I think clinically it's a very interesting field. It's really focused on the essence of making a diagnosis based on the data you have, which I really love. It's also grounded in technology, right? Which is great. So along the way, I think the deep learning wave started to really take off. I remember I was probably in my second or third year. residency, I started seeing all the research abstracts at RSNA, at SIM, really having a big focus on deep learning, on technology. So that definitely caught my attention, and I started to dive deeper. I took Andrew Ng's popular course on deep learning on Coursera, and that really kind of got the ball rolling. So towards the end of residency, Cornell has a great program, which is a body fellowship and informatics fellowship combined. So I decided to do that, and I worked with George Shi and Martin Prince on polycystic kidney disease segmentation. And prior to that, I had done some small deep learning projects. I had worked on kind of some small abstracts, working on like NLP related projects. But this was, I would say, like the first pretty mainstream, like kind of deployable model that I worked on over the course of a year at Cornell. And it definitely started off with like small baby steps, building a model that can somewhat detect where polycystic kidneys are. And I think this audience is a radiology audience, so I don't need to go into too much detail about polycystic kidney disease, but suffice it to say, it's a really important disease process to quantify on imaging. I actually didn't realize how important polycystic kidney volumes were to nephrologists prior to the project, but measuring that manually is really tedious. And actually, Martin Prince, my PI and mentor at Cornell, has a great demo where me and him kind of show the whole model in action measuring polycystic kidneys. So yeah, it was a really exciting project, and that kind of really locked my interest into working in AI kind of full time now as a research scientist at Tempus. But it definitely started off as like more of an exploration, and it took it from there.
Yeah, thanks for sharing that, Akshay. I think it's really interesting to think about how your journey has really been kind of this organic process of just kind of following what you're excited about and interested in. And the polycystic kidney disease project, I think it's super interesting. We'll get into that a little bit later. But for now, I'd like to ask you just some questions about your perspectives on AI in radiology in general. So one thing I think is pretty cool is you and I both kind of grew up as radiologists in the very early stages of AI when we were residents, then going into fellows. And this is about the time when computer scientists were saying things like AI will replace radiologists within 5 years. But now we fast forward to 2022 when radiologists are increasingly embracing AI as something that will augment them as opposed to replacing them. I'm currently here at the SIM meeting, and there's just so much here about AI, whether it's on the research side or on the industry side. So my question to you is, when you think about AI in radiology and how it's changed over the past 5 years, are you surprised with how things have developed? What have been some of the biggest successes that you've seen, and what have been some of the biggest hangups or challenges?
Yeah, so I think that's such a great question. I remember that time when that controversial statement came out, and I think that as radiologists, we realize there's a lot more to unpack than like a binary output from a radiology study. There's a lot of art to it. There's a lot of really generalized artificial intelligence, which is by no means solved at this point. Um, and I think you could potentially argue that solving all of radiology with AI is very much like solving general artificial intelligence, which remains a really open problem. Um, yes, over the last 2 years, I've been very impressed to see where the industry has been going. I think a few startups in particular have been publishing really exciting work in terms of larger scale detection of hemorrhage, looking at things like pulmonary embolus. I would love to see more publications, seeing how that translates into patient care ultimately, because that's ultimately what is going to really make a difference in terms of how we adopt AI clinically. But I think the technology is definitely showing a lot of proof of concept. As a radiologist myself, I realize that there are a lot of things that are easy for a radiologist to overlook. It could be a small area of disease. It could be hemorrhage. It could be something along the lines of that an AI model could help us identify. So I am excited to see how this ultimately translates to clinical care and kind of the clinical experience.
Yeah, I think the clinical deployment is certainly something that a lot of us, or probably all of us in radiology, are really excited about. But one of the things that you and I had talked about before is the need for infrastructures to support the development of these potential solutions in the first place. So things like applications or software to facilitate dataset curation, dataset annotation, as well as the model development and deployment. Can you talk about your perspective on the current state of infrastructure to support AI development and deployment? And what are some of the gaps that you see? And put another way, what are the opportunities ripe for disruption or innovation?
Yeah, that's a great question. I think that doing AI right now requires a lot of upfront work to set up the infrastructure for data curation, model training, model deployment, and the work we did at Cornell was really challenging in the sense that we kind of started from scratch and decided, okay, how are we going to process this data set of MRIs? How are we going to ultimately label those MRIs? What software are we going to use? And then ultimately, how are we going to deploy it? And it was really like each phase of that pipeline requires really good decision making. So yeah, so at academic institutions right now, I think it's really the Wild West. We have to kind of build everything from scratch, from data curation, data labeling, model building, model deployment. And each of those processes has a lot of complexity and a lot of decisions to make correctly. So at Cornell, with the polycystic kidney disease project, it was a really good experience kind of walking through that pipeline and building something. But I would like to see companies or research organizations publish frameworks that can make that entire process a lot easier. And that was kind of the motivation for RadLearn-AI, which is the project I started in residency. It was really tackling the data labeling piece of that problem. And just to give you a quick update on RadLearn-AI, it's still an active project, and I'm hoping to release a demo type of version that can be consumed on AWS or GCP. Really kind of as kind of a VM instance style deployment where someone can consume that within their own AWS or GCP infrastructure. But getting back to your main question, I think that the entire process of building models is really laborious for hospitals. And I would love to see organizations come together to make that process easier.
I couldn't agree more. I think that bringing the different stakeholders and different people with different expertises together is really key. But I think that's easier said than done. But you've been on both sides of the aisle, so to speak, as a practicing clinical radiologist and now as a senior software engineer for a precision medicine company called Tempus. So, based on what you've seen in these roles, is there anything you think that these two groups of physicians and engineers should know about each other that might not be obvious and maybe might make the difference in actually making this collaborative type of work a success?
Yeah, absolutely. I think it's very common for physicians to maybe underestimate the complexity of the engineering and the machine learning development, and vice versa. I think it's very easy for machine learning scientists to underestimate the complexity of the medicine and the disease. So I think, when you read a paper or you see something published, it feels like you have a grasp of the entire problem, but there's a reason I think these disciplines take a few years to really master and to really become an expert at them. So I think the most important thing is for groups to have like a multidisciplinary style collaboration where you have clinicians and machine learning engineers really collaborating at the forefront of projects. And I think the institutions that have done that well have really had high impact. And I think you can see that in the scale of their work. I'm sure a lot of the startups that have been successful are also doing that. And sometimes, they can be fortunate. They can have an engineer that has special expertise in medicine or a physician that has a special expertise in engineering. I definitely think those types of individuals can bridge the gap really effectively.
All right, let's shift gears a little bit to the study that you had mentioned previously. So, you recently first authored a study in the Radiology Artificial Intelligence Journal titled Deploy Deep Learning Kidney Segmentation for Polycystic Kidney Disease MRI. And in this study, you described development of not only a deep learning pipeline to segment cysts on kidney MRIs, but also prospective clinical validation of this model. You talked a little bit about this, but could you tell us a little bit more about the clinical motivations for our listeners who might not be familiar with kidney disease and how you developed and deployed the pipeline? And as a follow-up, what were your main findings?
Yeah. So thanks for asking the question. So this was a project that started off really as a deep interest of Martin Prince at Cornell. And the nephrologist really wanted to have an accurate assessment of how are their patients' kidney volumes changing over time. And the reason that's important is because if someone's kidneys are rapidly increasing in size, it might change their management considerations. It might have them put their patient on certain medications like tolvaptan. So, and measuring kidneys manually is really laborious, time intensive, requires specialized software. So, the interest was, can we automate this or semi-automatically do this using deep learning? So that was the motivation behind the problem. We were also fortunate that we had a lot of patients at Cornell with polycystic kidney disease, so we had a good amount of data. So the question was, how can we go about doing this and doing it at scale and doing it in a way that was robust? I think that last part of the problem, doing it in a robust fashion, is really important because what I think we all see, and I think this might lead to some of the skepticism in AI, is research groups publish results on models, but they don't necessarily validate them on external institutions, on prospective data, and they don't open source their models or their code to really stand by their results so other people can test the results. So part of the motivation of this project was also as a proof of concept to do research that could be validated prospectively and externally, right? To show that quantitative measurement using AI, in this case, with polycystic kidney disease, can be achieved, can be tested prospectively, and can be validated externally. Um, so really, I know I was a primary author on this paper, but it was largely a massive team effort. There were so many different aspects of this project, particularly when it came down to validation. I definitely took most of the ownership of building the model, training the first version of the model, and testing it. But when it came down to validation, it was a full court press. We had a lot of people helping creating ground truth on prospective data, on external data, to see how the model performs on those data sets. And I really give RSNA a lot of credit for asking some really good questions during the review process to really push us to publish something very rigorous. So I was very excited when this was accepted at RSNA, and I really think it came out, really well. So kudos to the editors there.
So I think that's going to be of a lot of interest to our readers who are hoping to publish in our journal to understand some of these potential, maybe not pain points, but maybe aspects of a study that lead to something very rigorous, something that allows for evaluation of robustness of the model. Can you talk a little bit about what some of those changes might have been and maybe
Yeah,
advice that you have for others doing similar kinds of studies?
yeah. So I think when it comes to medical data, we're typically limited by skill. And unlike a lot of public data sets that tech companies are working on that are derived from social media or the internet, medical data tends to be on the order of a few hundred, maybe if you're lucky, a few thousand samples. And what that means is that a lot of the things in deep learning that can be pitfalls, like overfitting on your training data, not being rigorous with the way you do training validation test splits, um, it's really easy to get those things wrong and to take kind of early shortcuts that might give you better numbers. And it's always nice to have better numbers for your publication. But then at the end of the day, your model ends up being very brittle when you start to try to deploy it and when you start to test it. And that can, I think, lead to like a lot of disappointment, understandably, because you can spend weeks or months of effort only to see that your model is not really translating to external data. So I think that um, it's really important to just really follow the fundamentals of deep learning, really down from how are you deciding your train validation test approach, making sure your test data, validation data, and training data all follow kind of a reasonable distribution. Um, Making sure there's no data leaks. So an example for like of a data leak in medicine could be like, let's say one patient has like a lot of MRIs and some of those MRIs are split across your test set and your training set, right? That would be a data leak that could really compromise your model results. So I think sitting down in the beginning, devising a strategy and doing that really well really adds up at the end when you start to say, how is my model actually doing in the wild? So I would say that's one really important piece. The second thing is having a strategy for testing your model on external data and on prospective data is really helpful, because the best way to get test data is to get test data that represents real world data. So if you have another organization that has data, you should almost ask for them to put it in a, storage area or a bucket and give it to you once your model is ready, right? That is such a nice form of validation because you're really showing translation to unseen data. And I think that's a really powerful way of doing this well. The other thing that's really important is having a statistician involved or having someone with deep kind of knowledge of statistics so you can make sure that you're reporting your model results in a way that is clinically useful.
Yeah, I've personally found that pretty challenging a lot of the time because you're talking about all of these different people involved, whether you're the clinician or the radiologist who understands why is this problem clinically useful? What are some of the clinically relevant performance metrics? But on the other hand, you have deep learning experts or computer scientists who really, as you said, understand the basic principles of even just something as simple as what is a training versus validation versus test split. I know that amongst radiologists and my colleagues, sometimes there's confusion about that because as you and I know, what we call a test split or a test set, that may be called a validation set in the computer science literature. And so I think that, and then you throw in statistics into the mix, I think then we've got three, different groups working together. Do you have any advice on how to really coordinate all of that? Because I think that in a lot of times we speak different languages. Sometimes we have different viewpoints, but you clearly were able to corral all of these different groups together. But I'm sure it was, you made it look easy, but I'm sure it was harder said than done.
Yeah, no, definitely. I think that it really comes down to having that interdisciplinary group where you have at least representation of all of that expertise. I will say that both clinicians and machine learning scientists do have training in statistics. It's fortunately kind of part of our biostats in medical school, and machine learning also puts a good amount of emphasis on statistics. So I think that if you have strong academic medicine and you have strong machine learning, you kind of cover your basis. In the case of our project, I definitely did a lot of um, self-teaching over the past 2, 3 years to develop the machine learning confidence to drive the project forward. So I was able to kind of cover both domains in terms of clinical and machine learning. I would be curious to know, right, how things at Maryland are being done or how things at other institutions are being done, because I really do think you want to have a seat at the table from both machine learning, from clinical and machine learning, so you can devise those strategies together and come to a consensus on how you're doing things to make sure that there's no confusion or there's no slips in the way you're deciding things in terms of, okay, what's the strategy for devising the data into train validation test? Sometimes I think what can happen, and I'm kind of imagining this, I haven't seen this happen, but I'm kind of imagining this, is that you could maybe silo tasks and say, oh, you're part of the medicine department, so you can give me the data in train validation test, and then I'll start training models on it. And then the medicine department or the radiology department says, sure, I'll prepare the data and I'll give it to you in those splits. But perhaps along the way, there was a lost communication on how to devise those splits, right? So that's just an example of like a small pitfall. I'm sure a lot of people know to avoid that who have experience in the area. But I really think having deep integration, right? So if someone is confused about something, they understand how to reconcile that. And on the flip side, I think if someone's training a model, they should really understand, okay, why is my model doing what it's doing? Why does a clinician really care about this? Do they care about the false positives? Do they care about the false negatives? Do they matter the same amount? How is this ultimately going to play out in a real world deployment? In the case of polycystic kidney disease, to get back to the paper, it really kind of ended up being a nice proof of concept because we didn't have to worry as much about the epidemiology in terms of like false positives, false negatives. We weren't working on a classification algorithm, if you will. Like we weren't trying to triage patients who have a rare finding. Like you could imagine triaging patients with stroke or triaging patients with pulmonary embolus. That's a very different type of question. And I think that can get into a lot more interesting discussions for how to set up that modeling problem. In this case, we were really trying to quantify a process that we knew existed in the data. So you have a patient, we know they have polycystic kidney disease. Now we're trying to measure which pixels are, disease, or which pixels are part of the polycystic kidneys and which pixels are background. So it becomes a semantic segmentation problem, which is kind of a nice, easy problem to model as a proof of concept. So I think that companies and research groups that are tackling more challenging problems in the sense that the true positives can be very rare in the data set, things like that. I think they can get into even more challenging ideas of deployment because when they're deploying things, they have to really consider the patient population. Are they upsampling for normals, things like that. So I do feel like our paper had a lot of things that made it practical to do within a group of, our team of 5, 6 people, obviously with a lot of external collaborators that could be harder, right, with more challenging problems.
Yeah, no, I think that's really interesting. And to answer your question, what we're doing at University of Maryland is we're doing exactly what you're saying. I am a co-PI of a lab with a computer science PhD who recently joined us as faculty. And as far as statistics, I can't say we have a full-time statistician, but like you said, I think that between me and my co-PI, we cover our bases, but then we do have some, shall we say, consultants on call as we need who have that deep expertise. So I'm with you there. And as far as the problems being of different levels of difficulty, I think it's really interesting to think about what are performance metrics, because I think sometimes in AI, we can get kind of enamored with the AUROC. That is a very convenient, I think, measure of performance. But as you said, for something like segmentation, although there is pixel level classification involved, that's not really the outcome of interest. And so, beyond things like dice scores and IOUs, I think one of the interesting metrics that you use in your study was not the performance or accuracy of segmentation, but the time required to segment the cysts. And in fact, I think one of your main results was that using the algorithm significantly reduced time required to segment cysts compared to human segmentation by 51%. And that's pretty striking, right? But how do you view time savings and other non-diagnostic performance metrics in relation to accuracy? Is one better than the other, or are they complementary?
Yeah, I think that's a great question. And I think it comes down to for every model you build, there are two types of metrics that you have to consider. One is your pure model metrics, right? In the case, it might be in the case of segmentation, right? Dice or intersection performance of the model is really important. You definitely want to consider true positives, like your overall results in terms of sensitivity and specificity, right? Definitely know that AUC curves, can have a lot of pitfalls. So important to take that into account. But I think the second type of metrics that are extremely important, and I'm happy we were able to roll this into our paper, is what are the clinical or the business metrics behind your model, right? And in the case of our paper, we were able to show that, the 50%, I was actually expecting it to be higher, a higher time savings, because I think there's a few outlier cases where we had to do quite a few corrections. But when you see the model kind of do that pre-annotation for you, it's really clear that it saves you quite a lot of work. And if you look at the demo video we made recently, I think you can get a sense of that. So that was an exciting metric that shows this actually has value to a clinical scientist or a clinical imager who has to annotate these kidneys. If they can save 50% of their time, and they do this perhaps a few hundred times a year, potentially at a large scale center, then that's a very meaningful time savings. Another metric, which we weren't really able to measure in the paper, could be how much better is your annotation using the model versus not using the model. And that's a hard metric to potentially measure because it then gets to the essence of what is your ground truth. We all know that human annotation is going to have some type of error just from your mouse movement, just from normal human error at the boundaries. Potentially model-driven annotation could be more accurate than human annotation. So I think getting to that question would be a really interesting follow-up exploration, which is, does model-driven annotation give you more accurate segmentation performance? So, I would love to see more and more papers kind of publish clinical benefits, right? What is the clinical benefit of the model? I think measuring that for a lot of things could be really tricky, right? So if you're a radiologist and you're really good at picking up brain pathology, your model might help you see that brain pathology faster. So I know a lot of companies are focusing on triage. So I think a really great metric might be turnaround time. So they could do A/B testing, test the model turnaround time with the triaging, test the model turnaround time without the triaging, and they could do things that way. Having the infrastructure though to do A/B testing in the normal packs is probably really really tricky because I don't think that's a core competency of pack systems right now. Unlike social media companies that do A/B testing hundreds of times per day, or probably more.
Yeah, and so speaking of clinical benefit, so much of AI has been relegated to proof of concepts, with relatively little in actual clinical deployment. And as we know, you've actually deployed this AI clinically, you prospectively evaluated it, effectively moving it from bench to bedside. But I'm sure there were challenges, things that you couldn't have foreseen. So, for the benefit of our listeners, what were some of the challenges and maybe lessons learned and words of wisdom that you might have for people hoping to clinically validate or even deploy it in actual practice?
Yeah, I think one really good thing that I realized in retrospect is it's nice if your first AI model that you're trying to deploy is very low risk. And that could be something that's quantitative, measuring something, for example, that you're going to measure anyways manually, because then the risk of bias is exceptionally low. You're not making a diagnosis, you're not classifying something. In the case of life-threatening problems in the ER, the risk of deploying those models is exceptionally high because if you bias a radiologist in one way or the other, that can be really consequential for patient care. So I think when your research group, if especially if it's your first model that you're trying to deploy, and I think for most research groups we're at that stage because it's still kind of early days, focus on something that is low risk that you can validate in a controlled setting, and that's going to be kind of run at a smaller scale. I wouldn't want to run an AI model on every patient in the ER to decide whether to admit or discharge or to decide whether or not they have pneumonia because you don't want to deal with the regulatory burden of doing that. I'm still actively very interested in that area. Actually, I have a lot of learning to do myself in terms of what's the landscape of deploying models that have clinical consequences. What's the regulatory burden required? I think we're all very excited about that area. And I think that this area is starting to mature as we speak and as companies are starting to explore that. I think that's partly the reason why a lot of startups are focusing on triage because the regulatory burden of showing an image to a radiologist faster, as opposed to biasing them, is very different. And you'll notice that a lot of the companies, if they triage a patient, they probably are not showing them the AI findings directly. They probably are just expediting the patient on their work list so they don't have bias in terms of when they're seeing the case. And I'm not 100% sure. Actually, you would know more than me now that you're at SIM and seeing all the demos. But yeah, I think that's a really important consideration. Like, what's the regulatory burden of deploying your model? Who are the stakeholders? In the case of polycystic kidney disease, we have a very controlled environment. Everything is always checked manually by a radiologist, and it's really a nice proof of concept controlled setting. But yeah, the next steps, I think we're going to be crossing those hurdles too as we start to ask ourselves, what are the other things we can do with AI? What are the other things we can do with quantitative imaging? Yeah, and the Cornell lab, I'm sure, is going to come up with a lot of great questions.
Yeah, totally. I can tell you just from one algorithm that's in use at our practice. Well, you do get the triage in terms of the images expedited, but you also get a heat map overlaid with a finding of interest. So, and I agree with you. I think there's some questions that still need to be answered, both from a clinical safety and a regulatory standpoint, for sure.
Exactly. But even the heat map, I think the heat map could potentially be very consequential in terms of biasing you. And I'll give you an example. The heat map tells you
potentially what the radiology AI model is focusing on, right? But it doesn't tell you the true confidence of the AI model, and you might not fundamentally know how precise that true confidence of the AI model is, right? And the idea is you ideally want to lock in your report, right? In the ideal setting, you sign your report, and then the AI model is triggered after you sign the report and saying, hey, here's a heat map I came up with, right? Do you want to change your report? Do you want to do an addendum? That kind of infrastructure at least forces you to lock in your clinical opinion before you start getting biased. And I think we can all, you can imagine when you're a junior resident and, your attending says, oh, do you see that? And, initially you might not have seen that subtle pneumonia or you might not have seen that atelectasis, but once they say, do you see that? And they point at it with their mouse, then you say, you often can see it, right? Things light up
Totally.
and you start to say, oh yeah, how did I not see that? Right. And as your kind of eyes get matured or as your visual cortex matures in terms of detecting pathology, we get better at that. And I think the key is that um, there are certain clinicians who I think are exceptionally well trained, and we all have subspecialty training in our own areas. But I think it's really important to understand that everyone has a different personality, and if you have an AI model put in front of 1,000 radiologists, some of them are going to be more susceptible to saying, oh, maybe I should be more conservative with my report because the AI model saw something here. Or maybe I should be, more defensive in my report because the AI model saw something here. So I think those are the types of questions that are extremely interesting. I think the startups in this space and the research organizations that are working on this have a lot of work cut out for them to understand how do we validate things in a meaningful way. And I think that I kind of came up with that idea during this conversation, which is okay. You have a report, you lock it in, and then you see the model and you decide if you agree with it or not, right? Potentially things like that could be really interesting. Another thing that could be interesting could be retrospectively showing radiologists things that an AI model did, so they don't have real clinical consequences. But yeah, I'm looking forward to seeing how this unfolds because I think there's a lot of open questions still in terms of how to do this well.
Yeah, I agree. There's a ton of open questions, and I think it's going to be an exciting future. So, speaking of the future, as we move into the last few minutes of our time together, I want to ask you a question that we ask all of our guests, and that is, what are you most excited about over the next decade in AI for healthcare, in radiology, or in informatics in general?
So I'm very excited about thinking back to my lectures on medical legal in terms of what are the things that radiologists have to worry about clinically. So obviously the number one metric is providing clinically useful reports. But I think the two things that really are issues for radiologists when errors happen are failure to detect, right? So failure to perceive a finding that is actionable, that is a problem. And the second is failure to communicate, right? Within a reasonable amount of time. Or so those are the two areas that I think AI could potentially make both of those things disappear. So I would love to see a kind of era when there's actionable findings, those are typically presented to radiologists. And it's never the case that there's a positive finding the radiologist just missed at the edge of the film. It could be a small PE on an abdominal CT, right? That you didn't see because it was at the very edge of the volume and you didn't notice it. And there's really like several clinical iterations that you could imagine, right? Where there's something that someone doesn't detect. And I think communication, this is really not an AI problem. Maybe it's just an infrastructure problem. But as technology advances, as a lot of companies are moving to the cloud, it would be really awesome to have much more efficient real-time communication with our clinicians. I think every radiologist can appreciate, how challenging it can be to reach a clinician at times in the ER when you have a positive finding. So I would love that whole process to be extremely efficient. So we can really improve both detection and communication. I think that will make a lot of errors in radiology as a field go away or get vastly reduced in scale. The other area I'm really interested in is unlocking quantitative imaging. And we essentially have so much information in our scans that we don't quantify, right? A lot of our things are subjectively measured. Is it mild, moderate, severe? How much disease is there? So I would love to see more research that quantifies different phenotypes. So in the case of polycystic kidney disease, we're quantifying volume, but you could imagine you start to quantify different features of those kidneys, like how much fluid is there, how much proteinaceous blood products or material is there in those kidneys, what is the actionable impact on prognosis for those patients, right? There's a lot of clinical questions to unlock, so I'd love to see that happen through advanced imaging, CT, MRI, PET. I think there's a lot of really interesting signal to further explore, and I think that could open up a really big need for radiology, because if we start to have, I should say, a larger need, because there's obviously already a very large need for radiology, which is growing. So I think quantitative imaging, quantitative research is going to be another exciting area. And just to give you a last area, is just technical improvements in how hardware works. I'm excited to see how companies innovate, incorporating deep learning in the way they're acquiring data, from the point of view of the scanner itself, and just from algorithms that potentially optimize MRI acquisition, things like that.
Well, Akshay, thanks so much. I'm really excited to see all those things coming down the pipeline. And I want to say again, on behalf of all of us here at Radiology Artificial Intelligence, thank you so much for joining us here on the podcast and sharing your perspectives as a radiologist, as a software developer, and as a startup CEO.
Thank you. I really appreciate your time. It was a lot of fun talking to you.
Likewise, Akshay. Thank you for tuning in to the Radiology-AI podcast. We'll be back next month. Be on the lookout for episodes like this and other content coming down the pipeline. If you like what you heard, please subscribe to us on Spotify, Apple, or wherever you get your podcasts. Please also follow us on Twitter at Radiology_AI. And if you have a topic or person you'd like us to cover on the podcast, email us at podcasts@rsna.org.